Oh, hello everyone. Welcome back to another Learning Glass video. Today, let's talk about heat pumps and the cycles thereof. So a heat pump is a pump for heat, which is a very imprecise vernacular from a thermodynamic theory perspective, but that's the idea, is that you put in some mechanical work into this cycle, and with the objective of getting heat transfer at high temperature to a room, to a space. So to get some high temperature heat transfer is the goal. You have to put mechanical work in, and because it's a heat engine in reverse, it's still subject to the second law of thermodynamics, which is it's a cycle, and with the objective of having heat transfer at high temperature, you're going to have low temperature heat transfer as well. And so that it's similar to the heat engine, but it's in reverse. So this would be a reverse heat engine. And another unique thing about reverse heat engines is that they use refrigerant. So another reverse heat engine is a refrigeration cycle. Another one is an air conditioning cycle, which are pretty much the same thing in terms of their operating conditions. There's just one is to cool a room, and the other one is to cool a box for food and other applications. So what it is, it's a reverse heat engine. So a heat engine for mechanical power burns a fuel or runs a nuclear reactor where you have some air mixture or some water that it's operating in a cycle. And the fuel, it gives you the high temperature, either the nuclear fuel or the combustion fuel, internal or external. It's a working fluid operating through a cycle of different steady flow processes. And reverse heat engines are similar in that you need a working fluid and it operates in a closed cycle. The unique thing about these reverse heat engines is that you need a special molecule that can reach low temperatures upon expansion. So you use refrigerant working fluid between hot and cold temperature. So the point of this reverse heat engine is to manipulate space cooling for either low temperatures or high temperatures. So a heat pump, you want the high temperature. A refrigeration cycle, you want the cold temperature. But they're both heat engines operating in reverse. For the heat pump, you're optimizing and designing your system for high temperature. But even though you want this high temperature for your space cooling applications, you still work around a refrigerant, which is designed to get to really cold temperatures specifically. So the refrigerant, even for the heat pump cycle, they get to sub-zero temperatures typically. And so what's happening for this heat pump, similar to a refrigeration cycle, is you have a high temperature branch and a low temperature branch. So and then you have to put mechanical work in. So let's show the low temperature branch first, which is the same as a refrigeration cycle. You have to have some heat transfer at low temperature. So this would be a heat exchanger. So here is a working fluid, and what happens is this is where the heat transfer occurs at low temperature for the working fluid. And what makes a refrigerant unique on this working fluid, it's that you have a throttle expansion valve. It's called the throttle process, which is some valve where you have some expansion from state 3, let's call it, to state 4. And upon doing that, you go to cold, from hot to cold. So that's what a refrigerant can do. You can have a high pressure here, high temperatures here, and then if you expand it through this valve, the pressure decreases and the molecule's response to that expansion to low pressure makes it really, really cold. It's a special molecule. Not all molecules do that. A lot of them do, but refrigerants do it very well. They have an extreme response to this expansion in the throttling valve. Then once you have this cold temperature in a refrigerator, this would be my seltzer here. So here's my nice Topo Chico new seltzers. And what happens in a refrigerator, refrigeration cycle, the refrigerant will be cold and it will be designed to get some heat transfer at low temperature from my seltzer to the working fluid. So this would be called the evaporator, because as we'll look on the phase diagram, when this refrigerant expands to cold temperature, it falls in this saturated mixture regime where there's both gas phase and liquid phase at cold temperatures. And the way that this cycle is designed is that after it expands at a given pressure to a lower pressure, it's going to complete the vaporization to all gas phase by boiling at, for a fridge, let's say we like our Topo Chicos at like 2 degrees Celsius. So that's pretty cold. So 2 degrees typically, and so that means a typical temperature for an evaporator in a refrigeration cycle is -degrees. That way you can transfer heat from hot 2 degrees Celsius to cold -20. So that occurs in the evaporation segment of a refrigeration cycle, which is designed to keep a space cold. And through a heat exchanger at this stage, this would be your cold temperature reservoir. Heat pump, it's similar but different. What the heat pump is doing, the objective is to get high temperature heat transfer. So instead of having the objective keeping my seltzer cold, what the heat pump is doing, you still have this heat transfer from the surroundings to the refrigerant, but what the objective is what you're doing is you have an outside, the low temperature reservoir, it's the outside air. So space heating is one of the major objectives of heat pumps. I have one in my house and it works pretty well. They used to not be that good, but they're pretty good nowadays if you can pay your electricity bill. It's a very electricity intense, but it does the job. And so here you have a flow of outside air transferring heat into the evaporator at low temperatures. So let's remove these specific temperatures for now, but you have cold outside air, and it's exchanging energy by heat transfer with the refrigerant to boil the refrigerant at cold temperatures still, but the objective is to get high temperatures. So what you do is when the refrigerant is boiled to the superheated vapor state, you put more mechanical work in. So this will be work into the working fluid refrigerant. So that would increase the enthalpy of the refrigerant and increase the pressure of the refrigerant. Then you get it to a higher temperature, higher enthalpy superheated vapor. Then you can do what you want for this heat pump, which is to pump heat, meaning that in the condenser stage of this cycle, you have high temperatures, hotter temperatures, and then you exchange heat by heat transfer to room heating. Room, air, space heating. So room, air, space heating. And let me make more room for the details. We're going to put some numbers on all of this stuff. So that's the objective, is room, air, space heating. And let's put some numbers on it. So at the room, let's call it a return of air So this will be some QH, heat transfer at high temperature. And that's what we want for this heat pump. And let's say for this specific process, this would be out of room, which is called the return. In HVAC and building, mechanical, plumbing, electrical, this would be called the return line, which goes into your cycle of where the room air, it's T return equals some colder temperature. Let's say the room, a room temperature started off at return temperature of 20 Celsius. And let's say this is all at 1 bar, isobaric, which is an oversimplification, but that pressure drop is not too extreme. And let's say we know here that the volumetric flow rate of the working fluid is 0.42 meters cubed per second. So that's our application. We are using this heat pump to keep a room warm by heat transfer at this condenser stage from the refrigerant to the room. And after this heating process, it goes into the room, which is called supply in HVAC MPE terms. And let's say that this temperature of the supply is now 50 degrees Celsius, which is pretty good. Still isobaric. Okay, so this is the application. It's a reverse heat engine, so we have to have this heat transfer at cold temperatures, and it comes from the outside air. So there's an evaporator unit outside. There's a condenser unit exposed to the room air by heat transfer, not contacting, but in a heat exchanger. And the way that we do this is a reverse heat engine operating with the refrigerant. So this cycle is going along the high temperature branch and the low temperature branch. This mechanical work from the compressor keeps this cycle going, and it's high pressure branch as well, and you expand it. The way that these are designed is you need a special molecule to work efficiently, that when you expose it to high pressure and then expand it in a quick valve, just a simple, just almost like a spray, it's almost like a spray nozzle. You just have a high pressure on one side, then you push it through to lower pressure. And if you do this to the right molecules, it'll get very cold, and you don't have to put a lot of work in, depending on the molecule. And which molecules are those? Well, let's call it, there's special molecules called refrigerants. There's one called that works really well called Freon. And let's put this little trademark because it's actually a company that has this brand name of Freon, and the specific one that we'll start off with is called Freon 12. Freon 12, the molecule, it's literally looks like this. It has one carbon, then it has a chlorine, and it has another chlorine, and then it has fluorines. So this is a chlorofluorohydrocarbon, chlorofluorohydrocarbon, and chlorofluorocarbon, CFC. And it's been banned. It works really well, but it's banned. You maybe can get it in TJ if you really want on the black market. And why is it banned? Because if you put this molecule and it leaks into the atmosphere has a molecule called ozone. And ozone helps us to protect it's in the atmosphere, and it helps to protect the surface, us and other things, from ultraviolet light. So ultraviolet light interacts with ozone, and it helps, and it blocks us from getting that ultraviolet light, which is bad. So we want the ozone layer. The problem was when there's too much Freon 12 in the atmosphere, then you destroy ozone layer, which is bad. That's why it's banned. And it worked. Ever since we banned this, our ozone layer has recovered, which is good. But interestingly, we still use something called R22 in the heat pump specifically. We use R22, which the brand name of it's Freon 22. And it's legal, and I guess they modified it to make it more mild. So the ozone depletion is not as bad, but that's good. The bad thing is that it doesn't work as nicely as this. Your AC doesn't get as cold, and you have to put more work in apparently because this molecule does not respond as well in the throttling as good old Freon 12 did. So I guess they replaced one of the chlorines with hydrogen, and that makes it more tame, which is good for the ozone layer. Not as well performing as the original Freon 12. And then there's another common one called R134A, and that it's two carbons. So it has a carbon, carbon. So there's two carbons. There's a fluorines, and it has some H bonds, and then these are all fluorines. So that's another refrigerant commonly used in HVAC, air conditioning. R134A, again, it's not as good as Freon, but I guess it's not going to destroy the ozone layer. So the one we're going to work with today on this problem is R22. So this is going to be an R22 working fluid cycled through the evaporation, the throttling valve, and this particular heat pump cycle, this reverse heat engine. So this refrigerant, it's going to get throttled to go to low temperatures when it expands. And so we put the numbers on the heating application. We want our room to return into this heat exchanger at 20 Celsius. If we run this heat pump correctly, we're going to be able to get 50 Celsius, which is pretty hot, pretty cozy, and to heat up this room at a certain flow rate of the air. And the question is, or that's what we feel, that's what it's designed for, but as thermal engineers, as mechanical engineers, we're going to learn that what actually happens is you need a right refrigerant that upon expansion will get to a really cold temperature, and if it's a heat engine in reverse, in this case for the heating application, it depends on what these other stages do as well. And by the second law of thermodynamics, to get this heat engine in reverse, you have to put some work in. There's not going to be any work out. The reverse heat engines, there's no work out at any stage, but there is work in required. And for a heat pump, you want the heat out as your application. For a refrigerator, you want this QC of their space as your application. And that affects the operating parameters. Okay, so to put more numbers in this, let's call this here state 1. So at state 1, the temperature of the refrigerant, we're talking about R22, is 5 degrees Celsius. P1 is 3.5 bar. So that's the low pressure branch. And that's the input to the compressor. And then after the compression stage at state 2, the refrigerant, not the supply, it's at 75 Celsius, and the pressure is at the high pressure branch, 14 bar. So the compressor increases the pressure from 3.5 to 14 bar, and that also increases the temperature. And what we're going to need to do is look up the property tables, the steam tables for R22 to get the ideas of the energies and enthalpies. So after the compressor, it does the application that we want, which is it's called a condenser because this starts off as the refrigerant working fluid at superheated vapor. Then by flowing through this condenser, the vapor refrigerant gets condensed to a liquid. How does it do that? It loses energy at high temperature to the room air. So the room gets hotter, but the working fluid gets colder. And that's what we want. We want to heat the room. So T3 here of the working fluid coming out of the condenser, it's 28 Celsius. So I'll draw that, give more room for that. T3 is 28 Celsius, and this is also isobaric here. So here, this is a room. Let's just neglect any pressure drop of pumping, of flowing through the ducts of a HVAC system, heat pump system. So this is going to be 1 bar of the room coming in, flowing into 1 bar of the room to supply a higher temperature air. That's the heat exchanger. How does that get hot? It gets energy from the refrigerant at the condenser stage of the heat pump cycle. It starts off as the refrigerant is 75 Celsius, loses energy, condenses to 28 Celsius liquid. Okay? Then the special part of these reverse heat engines is that if you pumped it up to this high pressure and you expose it to some expansion valve, just some quick or a nozzle that if it's high pressure on one side, low pressure on the other side, the response of this refrigerant molecule, it's going to get to a cold temperature. So let's not worry about that temperature. We're just going to say that here at after the other side, it's going to be the low pressure branch, and eventually after this evaporation stage by heat transfer, it's going to go back to 5 Celsius. So this is actually a little bit colder. This is T4 equals 9 Celsius. It's a little bit colder, but then when you evaporate, it's going to stay at 9 Celsius, but then we're going to go past the branch into the superheated state. So it starts off as a saturated mixture. We're going to verify that from the steam tables and the diagram. And it's going to end up as a superheated vapor, increase the temperature a little bit beyond this saturation condition. How does it do that? The outside air, it's hotter than 9 degrees Celsius. Oh, these are all negative, sorry, negative, negative, See the sub-zero temperatures here. So the outside air, it's colder, it's hotter than sub-zero temperatures, and you're able to evaporate. And then once you're at this stage here, you compress to keep the cycle going. So you put that work in. Okay, on a phase diagram, what you need is an R22 phase diagram, specifically or steam tables, and we're going to look at this graphically on a TS diagram. So typical reverse heat engines, whether they're vapor compression for air conditioning, refrigeration, or heat pump reverse heat engines, they operate on this refrigerant on the saturated liquid vapor dome, meaning that there's some regions of phase change between liquid and solid. And for a heat pump, the specific heat pump today, like I was saying, it's that it's going to operate around a low pressure branch. So this would be an isobaric line. Everywhere here, the pressure is 3.5 bar on this line. And there's a higher pressure branch where everywhere on this line, the pressure is 14 bar. So state one, it's the inlet to the compressor, and because we extended outside of this mixture region, the temperature is higher than 9 degrees. So let's say that this is 5 degrees Celsius, negative 5 degrees. And so -9 to -5. This would be the inlet to the compressor. And then let's neglect any entropy effects. So this would be an isotropic compression. So there's no delta S. It's just going straight up on this diagram to a higher pressure and higher temperature to state 2. So this would be the isentropic compression. Then what you want is at high temperature, have heat exchange to the room by condensing, losing energy from the working fluid to the room. By doing so, the temperature will decrease and the state will change from vapor to liquid to typically somewhere here, state 3. So you start at superheated vapor, you lose energy, you get into this mixture state, then you even go further to the compressed liquid regime. Then you have this so-called throttling stage. And at a throttling stage, so this is would be where you go to a low pressure. So it typically looks like this. At some change in entropy, you increase the entropy, but you decrease the temperature to go from a high pressure to a low pressure, and to the low pressure branch we started off with. So this would be the throttling phase. Then once you're at the low temperature, you keep the cycle going by taking in energy at low temperature. So this would be the evaporator where you're boiling off. Boiling, it is boiling, but it's at a cold temperature by bringing in energy from the outside, from cold to colder. The working fluid is colder than the surroundings. That's why the energy can go in this direction. Then to keep the cycle going, you put some mechanical work in as well. So this is the reverse heat engine, and the whole application would be to heat a room with this stage there. Okay, so this is the phase diagram, and similar to the steam tables, we can use a phase table, steam table for R22 fluid. It's a different molecule, as we said. It's this carbon, hydrogen, fluorine, no, 2 fluorines, and then chlorine. So that's R22. That's not water. Because of that, it has these different ranges of temperatures and pressures, and we like it because when you go from high pressure to low pressure, it's going to get a super low temperature. That's why we use these molecules. And if we look on a table, so let's analyze the stage from state 1 to state 2 by isentropic compression. This would be the first law, would be the mass flow rate of the refrigerant. The first law on the system of the refrigerant is what we're concerned with at the compression stage. We're also going to use that for the condenser stage, but the goal is to transfer heat from the working fluid to the room. But first, let's start at the compression stage. That will be the mass flow rate of the refrigerant times the difference in enthalpies of the refrigerant at the inlet and outlet. That has to balance the heat transfer from 1 to 2 minus the work transfer from 1 to 2. And next, let's simplify it by neglecting any heat loss at this compression stage. So, if we double check the superheated vapor table of R22 steam table, we would find that H1 and H2 are superheated vapor. And so H1 is, if we look on that table, it's 253.2 kilojoules per kilogram at 3.5 bar. H2 on the superheated table, it's 294.2 kilojoules per kilogram at 14 bar. So that we looked those up on the R22 table. They happen to be superheated vapor by comparing to the vapor of the saturation pressures and relative to the temperatures. Both of these lie on superheated vapor, as the diagram also shows. And we can pull out H1 and H2 from there. So from there, what we get is that H1 minus H2 equals negative the work. So we don't know the mass flow rate yet. So let's divide by mass to get work, baby W. So by using the R22 table values, what we get, it's that negative work equals 41. That confirms the work in at the compressor stage by using the first law. So that's good. Isentropic compression, okay. So next, after the compression stage, you go from state 2 to state 3, which is high temperature vapor to lower temperature compressed liquid at a steady flow. And so there, for the, let's do it over here, the 2 to 3 would be an isobaric heat transfer from the refrigerant being superheated to compressed liquid. And what's happening is the whole point of this cycle is so that we get heat out from refrigerant. Then that goes into heat into room air. So we're focusing on the cycle working fluid, which is the refrigerant, but that's going to connect to the room air. But first, let's just focus on the refrigerant, which goes from superheated to compressed. So again, the mass flow rate of the refrigerant times the difference between state 3 and state 2 enthalpies has to balance with any heat transfer at this stage and any work transfer at this stage. And here there's no moving parts, it's just a heat exchanger. So if we were to look at the R22 table, for compressed liquid, we would find that at this temperature, at this pressure, the R22 is at compressed liquid state. That would give us H3 equals, what is it? 79 kilojoules per kilogram. So the R22 at this state, it gives an enthalpy of 79. So that means that we can find the heat out of the, we can find little q. Divided by mass again, we don't know the mass. So the heat transfer out of there, it's 79 minus H2, 294.2. So that's negative 215.2 kilojoules per kilogram equals Q12. So that's good. That confirms that this is heat out. Negative value, heat out. So we use the steam table for that. That's good. Okay. So now let's focus on this application here. We just found what's happening to the working fluid at this pivotal stage. And we can also use the first law on the supply, on the room air, to see what the energies are involved in there. So I guess before that, we pretty much have characterized the performance of this, because like I said, what we want is heat transfer at high temperatures. What do we have to do? We have to pick the right refrigerant, and we have to put some mechanical work in. And that's how this so-called coefficient of performance is defined. This coefficient of performance, COP, it's one way to define this. This is also called beta in some other books or some online. Another symbol for that is beta. But by definition, it's what you want over what you have to pay. So what you want, it's some heat transfer at high temperature in the heat pump. This is a heat pump. So for heat pumps, and what you need, it's some work in. So we already found those. We found the work in that you need is 41, and what you're going to get out at these conditions is 215. So by plugging those in, did I even do that? I didn't have this number down. So 79, 215 over 70 over 41. That's pretty much 5-ish. It's like 5.2. Correct me for that number. I'm just doing it in my head here. 5.2. So we already have what we need there. But by the first law, you can also say for the cycle, or you can say that you can also express this in terms of the heat transfer. For the first law for cycle, delta H equals 0. So that means Q minus W equals 0. So that means you can say that the work in, the net work equals the net heat transfer. So you can replace this here with QH on top and then QH minus QC on the bottom. So we could also find coefficient of performance that way, but in this case we didn't need to, the way that we did these steps here. Okay, that's one note. Another note is that we didn't know the mass flow rate of the refrigerant. We do know the operation of the room air. We actually know everything about the room air already. We know we could have found the heat transfer into the room air by assuming the heat capacity of room air as well. So heat into the room air. So let's do the first law here. For the heat into the room air would be the mass flow rate of the air times the enthalpy change from the return side to the supply side. So that would be the enthalpy of the supply minus the enthalpy of the return air. So that will be the heat exchanger of the, focusing on the room air has to balance out with some heat transfer and work transfer, supply versus room. This is just a heat exchanger, so it's just that. And we could have made another assumption assuming Cp equals 1.005 kilojoules per kilogram Kelvin, which is a reasonable approximation at this temperature change, only 30 degrees Celsius. You can treat the heat capacity as 300 degree Kelvin value. So you can even say that the mass flow rate of air times a Cp of air times the temperature difference, delta T, from supply to room equals QSR. And that should be positive because the supply is hotter. But we don't know the mass flow rate of air. We do know the volumetric flow rate of air. Then we can use the ideal gas law. So we can say that the volumetric flow rate or the mass flow rate of the air by the ideal gas law, this is air, equals the pressure times the volumetric flow rate over the gas constant for air times the temperature of, this is the return given. So this is specified for the return side. Because of different temperatures, the volumetric flow rate is going to change according to the ideal gas law. So we can focus on a steady flow. The mass in equals the mass out. And as long as you're using the volumetric flow rate from and the temperatures corresponding to each other, you should be able to get the mass flow rate. So how we would use it here is that we don't know the mass flow rate of the liquid refrigerant on the other side of the heat exchanger. So what we can do there is say that on the mass flow rate on that side, we can say from a heat exchanger, the heat transfer at 2,3, that magnitude, in an ideal case, assuming there's no heat loss, all the energy from the condenser refrigerant goes into the room air, and let's call that the magnitude of heat at SR stage. And by doing that, we'll in effect be equaling this equation here. This equation has to equal this equation. So the mass flow rate of the refrigerant, refrig, has to equal the mass flow rate of the air. Assuming constant heat capacity, you can simplify it in terms of temperatures. So here it's a negative value, so we can flip that to make that a positive, because the magnitudes are what's the same. So the mass flow rate of air, we can use the first law for both sides, because we know the mass flow rate of air. So by plugging those in, we have all of this. We already know this. We could have found the heat transfer from the air from these values under this assumption. And we already found that heat transfer per mass using the steam tables per mass. Now we can find the mass of the refrigerant because we know the mass of the air. Because a cool way to think about it is, because we knew the total flow rate. So like another way of saying this is that here the mass flow rate of Q23 equals the mass flow rate of the refrigerant. So yeah, we know the total kilowatts. So let me write it here, I guess. Because we know the mass flow rate of air, we know that the total kilowatts, that magnitude, has to equal the mass flow rate of the refrigerant times Q23. So by knowing this already, we can find the mass we need to get this amount. That's what we're doing. And by doing that, you should find refrig, it's 0.07. Yeah. So that's what we did. That's another part of these problems, is that these heat transfer sections can give you these energy balances can be related to, can give you the mass difference between either side, because you might know the energy per kilogram, and then you need that proper mass to balance out the absolute value there. So that's what we did here to find the mass of refrigerant. So again, another way to think about it is, if you know the room capacity that you need, this room needs a certain temperature at this certain flow rate to keep it warm. The question now would be, what is the mass flow rate of refrigerant you need? That's what we did as well. Okay, so another note is what is this throttling process? A couple of interesting things about this throttling process. It's that you need, not all molecules have this response. They need to go from high pressure to low pressure, and the response should be a temperature drop. And the better refrigerants have a big temperature drop. That means you need to put less work in. If it has a big temperature drop, then you need to you don't need a strong compressor to go from hot to cold. So that's why these molecules are called refrigerants, because they go from hot to cold easier with less work required, less pumping required, less compression required. So for the throttling process, one unique thing is you always go from delta P is less than 0. It's going from high pressure to low pressure. And then delta S is you're always increasing the entropy. It's an irreversible process, always. You're always going to go have some crazy thing from compressed liquid to mixture at low temperatures. Another unique thing, it's that to simplify it, we say it's isenthalpic. The enthalpy doesn't change that much. And that simplifies the first law as well. We also say that the Q equals 0 and work equals 0. And that's why that leads to this isenthalpic simplification. Then what's typically in a typical refrigeration cycle, what happens is Hn equals, it's a mixture. So this would be saturated mixture. So that means it's there's some quality involved. So there's typically a quality at the outlet, and you balance that out according to whatever the steam table will give you that row with the enthalpy you had coming in. So those are some unique things about these heat pump cycles. There's a lot of similarities with refrigeration cycles. They're both reverse heat engines. They both operate around these refrigerants, and they both have these throttling conditions here, and they have these mechanical work requirements as well. All right, so thanks, and I'll see you guys next time.